Okay, and so welcome. This is an introduction to time series econometrics. This is really just going to be like a quick little crash course to make sure that you guys know what's going on when we talk about some of these empirical tests for the real business cycle model and then the upcoming new Keynesian model. So it's not going to be like that bad. You're not going to have to know how to do any statistics or anything of that nature, but you're it's going to help us figure out how we're going to tie some of these theoretical models to the real world, because so far all that we've seen is just a bunch of, well, here's a cool theoretical prediction for what should happen in this model, but we're not really seeing um, how that's tying into the real world. Like, are these models any good? So basically, we're just going to take some statistics. Again, you don't have to know how to do these statistics. You don't have to know how to find the mean of any of these things. You don't know how, or you don't have to know how to test to see if like there's a stationary time series process or estimate any of this stuff. You don't have to do any of that. Basically, I'm testing the model, and we're going to be looking at the predictions of the model. Now, I know you saw some static representations of this when we were looking at like different types of shocks in the real business cycle model. Those were static shocks. These are dynamic shocks. So what we're doing is, well, the RBC model is in its base form a dynamic general equilibrium model. So if it's a dynamic general equilibrium model, it would stand to reason that the empirical tests of this should also be dynamic, meaning we need to use time series data. And we're going to be fitting the time series data to time series models that would match with the real business cycle model, and then we see if it fits. If it fits, great. If it doesn't, well, we got a problem. So let's talk about what time series are. So a time series is a variable that evolves over time. It's got one observation per time period. The models that we care about look at variables that are functions of one or more lags of themselves plus some error. Basically, it says past behavior predicts future behavior, but it doesn't do so perfectly. Now, we're going to assume a mathematical form of the statement that past behavior predicts future behavior through what's known as an autoregressive process, or an AR process, or ARP for short, is a representation of a random process that is a function of past values of itself, where P is the number of lags in the ARP process. And it looks like this if we have an AR1. So there is one lag because we've got YT equals is alpha naught plus alpha 1 times yt minus 1 plus epsilon t. And we're going to go through what all of these different components are in this AR process. So let's start with alpha 1. Well, alpha 1 is the slope coefficient of yesterday's, or really just the previous value. It doesn't have to be yesterday. It could be last week's, last month's, last quarter's, last year's, whatever. But if it follows an AR1 process, then the relationship between what the value was yesterday and what the value is today is going to be reflected through that alpha 1. Right? It's the amount of yesterday's events that affect today's events. The alpha naught term is the initial condition, and then this epsilon t is the residual. Now, the values of alpha naught and alpha 1 are constant every period. In other words, they're time invariant. So if something is time invariant, it doesn't matter what point in time we're at in this particular time series, because that coefficient, that value, that parameter is going to be constant. It's going to be the same every single period. But this epsilon t is the residual, and it changes each period. So if you want to think of it this way, if you see a t subscript ever attached to any of these particular values, it can change each time period. If there isn't a t subscript, so like the alpha 0, alpha 1, right? There's no t subscript, meaning that they don't change over time. So they're constant over time, hence time invariant. Now, this epsilon t is the difference between what is estimated and what the real world is delivering. So let's drive this home through an example. If I had a model looking at how much NyQuil I like to drink on a daily basis, it would maybe look something like this. Okay, so I suppressed the initial condition. Don't worry about it. Just think about it like this right here. This alpha 1 is the slope coefficient of yesterday's amount of NyQuil that I drank. And alpha 1 is assumed to be between the -1 and 1 interval along the real number line. You don't want it to be larger than -1 or larger than 1 or less than -1, or we can say just in magnitude, right, contained on the 0-1 interval. If it's larger than that, we have a problem, which we're going to get to in a second. But if, say, alpha 1 is 0.95, then the amount of NyQuil that I had last night is going to determine 95% of my decision making tonight when I figure out how much NyQuil I want to drink tonight. So think of it as like a habit thing, right? Or even like an addiction thing. So from this, right, this alpha 1 yt minus 1 is what's known as the deterministic component of this equation. If something's deterministic, it's been determined already. There's nothing in the real world messing it up. This is the stuff that we can predict, the stuff that we can try to forecast. But this epsilon, right, the residual tells me the error that gets introduced from the real world. This is what's known as the stochastic component of an AR process. Basically, it's the shit happens part of the model. And it tells me what the difference is between what the model predicts and what actually happens in the real world. So by looking at that, we're going to be able to determine, all right, well, we can look at a shock to that epsilon t, and we're going to see how the rest of the model is going to be responding accordingly. And if it responds in a way that's consistent with what the economic theory suggests it should be, then, well, okay, we probably got some decent theory, and there's a good econometric test to show or to provide evidence that it, oh my God, what the hell is that? Okay. Anyway, so we have an equation talking about how much NyQuil I like to drink. Maybe I should slow down, because if I'm seeing stuff like this, maybe it's a sign that, stop drinking as much NyQuil or something. I don't know. Probably won't learn from my mistakes. So if this alpha 1 is 0.95, then every day, basically the amount of NyQuil I drank last night determines 95% of the amount of NyQuil I will drink tonight. But let's say I have a really bad day, like my girlfriend leaves me because I drink too much NyQuil, or I got fired. Well, actually, I haven't gotten fired. I got laid off, but I've never been fired from a job, so there's that. That's nice. Or, Bill Lumberg took my red swing line stapler off my desk, and now I want to I always just set the building on fire. Yes. So, little things. Something good or bad happens, and you didn't expect it, right? Because that part isn't really included within the model. If you didn't expect it to show up, well, when it does show up, it shows up in that epsilon t. It represents a source of shocks to the system. It's exogenous to what's estimated in that alpha 1 term. So if you have a bad day and you want to drink more, or you have a good day and want to drink less, or who knows, maybe more, it gets reflected in that epsilon t. So epsilon t has a distribution. It's assumed to be normally distributed with a mean of 0 and variance of 1. Now, don't worry about any of these statistics. You don't have to find the mean of any of this stuff. Don't worry about that. You don't have to find its variance. Just know that it has a mean of 0 and a variance of sigma squared. But again, we're not getting into the weeds on that stuff. So if I drank 3 ounces of NyQuil last night, and I had a pretty rough day today, then let's say, because my day sucked, epsilon t is going to be 2. So basically what that means is I will be drinking 2 additional ounces of NyQuil tonight. So if I plug all that stuff in, 0.95 is that alpha 1 parameter, right? Multiply that by the amount of NyQuil I drank last night, which is 3, plus that epsilon, which is 2. Well, that gives me 2.85 plus 2, which is 4.85 ounces of NyQuil that I will be consuming tonight. Tomorrow, I have a significantly less awful day. In fact, it's actually quite good. So because it's good, that epsilon t is going to be below 0 because I'll be drinking less than what I am on average, right? So I would take the yt value, right? Update the whole AR equation 1 period. So I got yt plus 1 equals alpha naught times yt plus epsilon t plus 1, right? So what this tells me is I got 0.95 times 4.85, the amount that I drank today, for tomorrow, minus that epsilon t plus 1. So it says epsilon t equals negative 0.5. It should be epsilon t plus 1. That was my mistake. Don't sue me or leave me bad evaluations on Canvas, please. I don't know if I'm allowed to say that, but I just did, so oops. So anyways, this tells me that I'll have 4.11 ounces of NyQuil tomorrow. Now, let's say I don't have any more good or bad days. I just have days. They're neutral. How long is it going to take for me to revert to how I normally behaved while drinking NyQuil? Well, to answer that, I need a steady state, right? How I behave absent any shocks. Is the steady state stuff kind of starting to seem familiar to you guys now? Because this is an empirical representation of what this is, right? The steady state for this guy is when the shocks are going to be 0 and the amount of NyQuil that I'm drinking is constant over time, right? So if I want yt plus 2, t plus 3, t plus 4, t plus 5, right, when epsilon t plus 2 equals 0, right? Well, yt plus 2, I just plug in what I had for yt plus 1, I get 3.9. Yt plus 3, plug in the 3.9 from yt plus 2, and I get 3.7. And again, that epsilon term, that shock, is 0 because it's a neutral day, right? It's an average day. And because it's average, or its mean, is assumed to be 0, if I have an average day, I'm not adding or subtracting any ounces of NyQuil to my consumption. So yt plus 4, well, I take that 3.7 output from t plus 3, plug it in, get 3.5, go forward, one more, 3.3. Now, I could keep evaluating this thing over and over and over, and I'd really want to know what that would be as I approach, or as the time horizon, we'll say, in the future approaches infinity. And that would tell me what the mean of this process would be, like what it would revert to. And the mean in this case is 0, which means that absent shocks, I don't drink any NyQuil in the long run. But in the short run, if I drink a lot one day, I'm going to drink a lot the next day, but a little bit less, and then a little bit less than that the day after, so on and so forth until I reach 0 NyQuil consumption in the long run. All right, this makes the AR process mean reverting. The size of that alpha 1 captures the persistence of the process. The bigger alpha 1 is, the more persistent the process is, and the longer it's going to take to die out. So if you want to try it on your own, let alpha 1 vary. Say alpha 1 is equal to 0.1 and compare what that does to alpha 1 equals 0.6, right? And like I said earlier, it needs to be between -1 and 1, but not including -1 or 1 for this to work. In that case, we have a stationary time series, and that coefficient alpha 1 is in between -1 and 1, not inclusive, so it's an open interval. So what that means by an open interval, just for anybody who's kind of curious, if there aren't like a bunch of real analysis nerds out there like me, along this open interval, you can get infinitesimally close to either -1 or 1, but you can't actually touch -1 or 1. So there's always some neighborhood of, say, epsilon, where epsilon is arbitrarily small yet larger than 0, where you can just add that epsilon to wherever you are and get a little bit closer to either -1 or 1, and still not actually touch -1 or 1, right? So if alpha 1 is contained in this open interval, right, it's said to be a stationary time series. So the time series has a constant mean and variance. Now, if this time series stationary, a nice way to think of it is you can just draw a straight line through it, right? So this is a stationary time series. You can see that, yeah, okay, it bounces around quite a bit, but if you were to just basically draw a straight line through like the middle of it, well, yeah, that would be a stationary mean, and it would have constant variance. But remember, right, gross domestic product grows by the following process. 1 plus gamma times what GDP was last time, plus now we're introducing error, that epsilon t. But if this gamma is the growth rate and it's positive, then the slope coefficient for this AR process would be larger than 1, meaning it's not stationary. Not stationary means you can't draw a straight line through it, meaning there's no stationary mean, there's no constant variance, and it would actually look like this. All right, that's not very good, is it? It's good because we can see real GDP is growing over time, but we want it, if we're going to model this thing, unless we want to include some more like particularly advanced techniques, this guy needs to be stationary. So there's a lot of problems that come with this, but if you want a mean reverting AR process, non-stationary process doesn't have a constant mean, so it's not mean reverting. So there's no stationary state, there's no steady state. It just keeps growing and growing and growing, and it doesn't ever return to what it would be at rest. Now, like I said, there's a lot of ways to go around this issue. We could convert GDP into a growth rate, which converts it into a percentage change from each period. That growth rate could be stationary. So if this is GDP, right, so I'm suppressing epsilon t, so just don't worry about that. Think about just the yt equals 1 plus gamma times yt minus 1. Well, if I subtract yt minus 1 from both sides, this is what I get, right? So if I go ahead and distribute that yt minus 1 through the parentheses in equation 9, right, I get yt minus 1 on the left-hand side. On the right-hand side, I have gamma yt minus 1 plus yt minus 1 minus yt minus 1. So those last two terms in equation 10 plus yt minus 1 minus yt minus 1, well, that gives me 0. So if I first difference this, right, I'll get a stationary AR process. But that's just the first difference, right? Suppose I want the percent change. Well, it's new minus old over old. So if I divide both sides by yt minus 1, I get this, just gamma. So for a time series in the form of a percentage change, it would look like this if I took the natural log of the stuff across. So again, minor mistake, don't worry, you don't really need to, I'm not going to be asking you this on an exam. This is just to give you a nice little introduction into some time series econometrics. It would be in log differences. If I did the first difference of the natural log of this variable, right? So the first difference of the natural log is a percent change. Boom, what do you know? If I look at the percent change in real GDP, or the log difference of real GDP, this is what I get, stationary time series. In fact, this is actually the stationary time series that we saw a few slides ago. You can draw a straight line through it, constant mean, constant variance. Good stuff, makes me happy. So to be able to actually test some of these existing dynamic models, remember there were a bunch of different equations, right? We had like a labor supply, labor demand. We had a production. We had like aggregate supply, aggregate demand. We had money markets. We had the Euler equation. We had all these different equations showing up, which means I have a system of equations, and I can't get a system of equations in just one particular equation. It doesn't work that way. Now, it'd be nice if it did, but it doesn't for, well, a lot of reasons. So let's take what we just saw with the AR process and just put it in a multivariate form, right? Basically, it's a univariate time series. Well, it's like a univariate time series, but we just have more equations, and thus we have more variables. So if I had an autoregression or an AR process, and I wanted to have multiple of these things that were estimated simultaneously, I get a vector autoregression, or VAR. This VAR, let's say I want to have two equations with two variables. Now you can have n equations with n variables as long as you have enough data to be able to estimate it, giving you a sufficient number of degrees of freedom. But that's, again, getting a little further into the metrics than I want to get. It's just something that if any of you are familiar with this stuff, if you are familiar with econometrics, I just wanted to get that out there just in case you were asking questions. So instead of, let's say, we're just playing with output or GDP, I'm also concerned about the price, right? Think of this as modeling like a dynamic aggregate demand and dynamic aggregate supply curve. So I have an autoregression equation for output with one lag for output and a lag for price, and an AR equation for price with one lag for price and one lag for output. Right? It would look like this right here. Right? So equation 16 says output is a function of lags of output and price plus error. Equation 17 says the equation for price is a function of lags of output and price plus, well, some other error. Now these epsilon t terms in equation 16 and 17 are not the same. I have an epsilon y in equation 16 and an epsilon p in equation 17, right? So any source of outside shocks, we'll say, would enter through that epsilon y in equation 16 if I want a shock to impact output. For any shock to the price level, right, that would be driving through the epsilon p term in equation 17. So I'm just going to estimate a VAR using some monthly data from January 2008 to October 2018. And I get these variables from the Bureau of Economic Analysis, BEA, which is recorded at a quarterly frequency. There's also an awesome company called Macroeconomic Advisors. They take quarterly data and they use cool methods to increase the frequency up to monthly. So where I initially had quarterly data, thanks to macro advisors, I can actually use monthly data, which gives me more data to play with, right? I have more degrees of freedom for those of you that have had econometrics. Now, for the price level, I use the Personal Consumption Expenditures Index, or the PCE. This is the price index used by the Federal Reserve when determining monetary policy. A lot of people like to use the Consumer's Price Index, but as a monetary economist who understands what the PCE index is, and the Fed uses that one rather than CPI, I'm going to use what the Fed uses. Now, we can make some matrices out of this VAR thing to make it look a little bit cleaner, right? So if I want to clean it up a little bit more, I can just throw the stuff in here. Boom, gives me that. So in equation 18 also, there's another little mistake. There's not supposed to be a plus between this and this. It's actually supposed to be a times. So I messed that up. But at least I addressed it. So just pretend that's a times, not a plus. But if I clean this stuff up, basically I get equation 20, which is the exact same thing as this, which is the exact same thing as these two guys right here, just put in a different form. So if you ever see any of this stuff on an exam or homework or anything like that, you will see equation 20 in some way, shape, or form. You don't have to know how to do this stuff. You just have to know that this is a vector autoregression. Now, the reason that we care about this stuff, right, the reason we want to be able to test this stuff is because of that epsilon t, right? That thing holds all the information regarding the shocks that we've been studying thus far. Right, so that shock to epsilon y is a demand shock. The shock to epsilon p is a supply shock. So if I were to shock this epsilon y, I'd expect to see output and price move in the same direction. Right? If there's an aggregate demand shock, output goes up, prices go up. There's an aggregate supply shock, on the other hand. I would expect to see output and price move in opposite directions. So a demand shock should look like this. A supply shock should look like this. Right? So here, output and price move together. Here, output and price move in opposite directions. But I want the dynamic responses to the shocks. These are static, right? There's no time period here. It's just, well, there is a time period. There's only one. There aren't multiples. I want dynamic. I want dynamic. Sound like a petulant child. But what we just saw were the static responses. So if I want to see how the price and quantity respond over time, well, I need something called an impulse response function. And this comes either from a shock to that epsilon y, or epsilon p, and I will plot how the equations respond over time. But we've got an issue here, and that's what's known as an identification problem. These residuals are correlated with each other. So that means if I were to look at a demand shock, I'm picking up stuff from that supply shock, and vice versa. That's not good for me, right? That's actually really, really bad, because we can think of it as, if we're looking at these shocks, the way they're currently set up, they're contaminated, right? It's not purely a demand shock, and it's not purely a supply shock. So I got to figure out how to make them not correlated anymore to basically get a pure supply shock and a pure demand shock. Now, there's a bunch of different ways to do this. Everyone has their own thoughts on which one is the best. Don't worry about the method that I use, because all you have to do for any of this stuff is just interpret the results. And the idea to be able to identify this stuff, where we want to identify these shocks. So with like the real business cycle model shocks that I talked about, where it's like, can we identify, a technology shock from a labor supply shock, right? This is basically what I'm talking about. I want to be able to do that. I want to be able to make sure that I'm identifying these shocks in a way that's consistent with what the theory suggests. So I can take that economic theory and I can impose just enough restrictions to ensure that the shocks that I'm looking at are fundamentally different from all the other shocks. So I need to put this guy into a structural form. What we originally saw was a reduced form VAR. I want a structural VAR, SVAR. Right? So this SVAR is really the true link between a dynamic stochastic general equilibrium model and the real-world modeling with real-world data. So I take the results from the DSGE and I use that to guide the way I'm going to be imposing restrictions on the VAR, which lets me test if the DSGE works, right? If the model produces some impulse responses and the SVAR produces the same impulse responses, then it's a good model. But if they don't match, they're not the same, I need a new model. Right? So to identify this, I use something called sign restrictions. It's a pretty cool Bayesian way of identifying these things. But the nice thing is that while the math behind it and the programming behind it is an absolute nightmare, hence why my dissertation took a while, the intuition behind it is incredibly simple. If I want a demand shock, I want a positive response in price and a positive response in output. So if I go through and I sample this stuff, right, every draw that I make, if I get a draw with impulse responses where output and price move in the same direction, boom, that's a demand shock. If I make draws and I get them moving in opposite directions, boom, that's a supply shock. And so because I am imposing this economic theory that is an incredibly strong, robust economic theory, right, the law of demand, it's pretty easy to then take that very strong assumption and apply that to the data that I'm looking at. So I just sample from a bunch of draws from this structural form that's consistent with the reduced form, right? Because there's a lot of structural forms, but I'm concerned about the one that is like the best, right? So I'm not going to get too far into that, but basically we can do a bunch of algebra to recover a structural form from a reduced form. There's like a continuum of structural forms. All these draws where output and price increase are stored as a demand shock, right? We just draw, go, hey, demand shock, cool. Throw it back in the pile, go back to the pile, grab another one, see what it does, right? And if everything's moving in the same direction, then it has to be a demand shock. Output and price move in opposite directions, on the other hand. When I make that draw, I store it as a supply shock instead. So for a demand shock, I use sign restrictions to impose a 1% increase in that epsilon YT. So I'll see real GDP increase by 1%. And I want to see how much the price level will increase. For a supply shock, I use sign restrictions to impose a 1% decrease in prices, right? So there's a 1% reduction in the PCE, and I want to see how much real GDP increases after that. So here's the demand shock. All right, so let me tell you how you need to interpret this stuff. We're assuming, so this is at t equals 0, and this is the number of months going out after the initial shock. The shock hits, it holds for one period, and then I just let everything sort of respond to that shock. So what happens? Well, let's actually ask ourselves first, what happened before the shock? So as you can see, this is at t equals 0. If I have t equals -1, -2, -3, -5, -10, whatever, it was going all along a flat line, right? So this black line here, the x-axis, really it's a t-axis for time, it was flat. It was flatlining, and then boom, at t equals 0, the shock hits, GDP increases, and then sort of decreases a little bit, but it stays above 0. How do I know that it stays above 0? Well, first, I look at the y-axis, right, the vertical axis. If it is above 0 in the vertical axis, right, this red line here that I'm looking at, that guy's above 0 on the vertical axis, well, then it is above 0. Real GDP is above 0. Now, you're probably wondering, okay, what's up with this red thing and these like purplish bands around that? Well, this red line here is the median of all of the impulse response draws that I took when I did that sampling stuff. So I get this whole distribution of these things, and I take the median of that, the median draw. I take the median draw because there could be cases where the mean draw wouldn't actually exist. But the median draw does exist, right? Because if you've got a bunch of data and you want to find the mean of it, the mean may be an element of your sample, right? It might be an observation in your sample, but it may not. And I kind of want to have something that's an observation in my sample, so I take the median because the median is always going to be contained within your sample. That's why it's the median number. But the stuff around this, right? This is a 68% Bayesian credibility band, right? If you've had statistics, think of it as a confidence interval. The interpretation's a little different because it's Bayesian, but the idea is still the same. It's basically a confidence interval. What this tells me is that 68% of all the draws that I make where real GDP increased, 68% of all those draws were above zero. If I were to get the 95%, the bands would be a little bit larger, right? They would kind of be like this for the upper end and like this for the lower end, but they would still be above zero. How do I know? Well, because I've looked at it. So by looking at this, right, if this guy goes up, if GDP increases, and then the lower band here is also above zero, that's evidence to suggest that real GDP actually increases in response to a demand shock. Right? Let's look at the PCE index here. Again, it was going flat until t equals 0. The impact hits, the shock hits at this point. It increases on impact. Right? You can see here GDP increased to 1%. So how much do prices increase? Well, on impact, right, they go up by about 0.25%, and they peak at just a little above 0.4% above zero. Now, this is also a significant, or like a significantly positive response, so to speak, because this lower band is above zero. So the median impulse response draw is what you're going to be interpreting if I ask you, hey, how much does GDP go up and how much do prices go up in this particular case? You would look and go, all right, I would want the maximum response of each one. So the maximum response of GDP is 1 percentage point above zero. The maximum response of prices is about 0.4, like 1-ish percentage points above zero. And we can be pretty sure that this is a significant response because 68% of my draws in both cases are above zero. And they're above zero for the entire time horizon, too. This guy never crosses zero here, never crosses zero here. So this is a significant response to an aggregate demand shock. All right, let's look at a supply shock. All right, here, prices fell by 1 percentage point. And I want to see what happens to real GDP. Well, if prices fall by 1 percentage point in response to a supply shock, we're going to see real GDP increase by almost 3 percentage points. That's pretty substantial. That's a pretty large response of real GDP. So we can see there's a massive response of real GDP. Its maximum response is just shy of 3 percentage points, and it kind of starts to trend back towards zero after a little while. When we look at the PCE index, right, well, this is a negative response here. So if it's positive, I want this lower band to be above zero for at least some point so I can say there's a significant response of this thing over the time horizon that I'm looking at. For prices, where they drop in this case, I want this upper band to be below zero. So if the upper and lower bands are both below zero and the median impulse response draw is, well, also below zero because it's going to be contained between these bands, it's always going to be the case, then what we can say is we have a significant response of prices and output to a supply shock. So if these bands, if there's an increase, if the lower band is above zero, if there's a decrease, the upper band is below zero. So the lower band here has to be above, upper band here has to be below. You might want to take a note of that. If we can see that basically a majority of these draws are all here below zero and here above zero, then we're in good shape. So now what we're going to do, now that we've covered this, is use it on the real business cycle model. You're going to see how we do this really soon, like later today. But until then, well, that's all, folks. Thanks for watching, and I will catch you on the next lecture. So take care.